Okay. Thank you, Juan, for the introduction. Yeah, I'm CEO from Purdue, and this is a joint work with my colleagues from U of Iowa, Musa and Omar, as well as my advisors, Aniket and Ninghui from Purdue University. So in this session, we have seen a lot of great examples on low-level memory safety kind of issues, right? Low-level errors. So in this paper, we try to kind of look at a somewhat orthogonal but complementary problem of logical errors, right? Because bugs can also manifest at the semantic level, obviously, right? Especially when the software implementation deviates from the specification's requirements, right? And these logical errors have been found to enable non-trivial attacks. For example, I think recently there's a authentication bypass found in libSSH, and these logical errors can also lead to all kinds of, say, crypto attacks. So in this work, we kind of try to promote and advocate that symbol execution is good for analyzing semantic correctness, right? In general, symbol execution gives you a somewhat good code coverage. And even though it has some scalability challenges, we show you that with the help of some domain knowledge, you can actually use symbol execution to do meaningful analysis in terms of semantic correctness. So as a case study in this paper, we look at the problem of implementing PKCS version 1.5 RSA signature verification. The motivation of looking at this particular problem is very simple, right? PKCS version 1.5 RSA signature is widely used on, say, X509 certificates, in SSH, in IPsec, and in many, many other protocols. So there are some previous papers looking at kind of how X509 certificates are being validated, but I think none of them actually looked into RSA signature. And when it comes to RSA signature verification, it really depends on the implementation to verify signatures robustly, right? And it has been reported by other researchers that logical errors in these signature verifiers can lead to signature forgery, right? So let's quickly review the textbook RSA signature, right? So the signer, in order to sign message M, compute hash of M, of course, and then raise it to D mod N, where D is obviously the private exponent, N being the modulus. And then the output of that would be your signature S. So the verifier now given S the signature, M the message, and the public key to verify whether S is a valid signature for message M. The verifier simply takes S, compare S to E mod N, compare hash of M, and see if the two matches, right? So very easy, very simple. That's probably actually why RSA signature is being widely used because of its simplicity, right? Unfortunately, reality is usually much more chaotic and messy than what you would expect, right? So the first problem here is that what hash function you are going to use as a verifier, right? There's so many choices. SHA-1, SHA-2, whole family of functions, SHA-3, whole family of functions. Which one to use? And then the second problem is that the size of the modulus is usually much, much longer than the hash output, right? So nowadays, it's actually rather common to have a modulus at least 2048-bit long. But SHA outputs are rather short comparatively. So what you need is some padding and some metadata describing the hash algorithm, right? So that's actually why we have this PKCS1 family of standards. So PKCS1 defines both encryption and signature schemes. And even though the newer versions of PKCS1 adopted some schemes from Bleichenbacher, as of today, I think for digital signatures, version 1.5 is still the most widely used scheme. For example, on certificates of Google and Wikipedia, they're all signed by this version 1.5 signature scheme. So now the signer to sign message M, instead of doing hash of M to D mod N, the signer would do K to D mod N, where K looks like this. So K contains an initial 0, and then a block type, which for signature has to be 01, followed by padding bytes, which has to be FF all the way, at least 8 byte long, and you pad K to the size of modulus N. And then in the end of K, you have AS, a DER encoded ASN1 object, containing metadata describing the hash function you choose, and the actual hash of M. So if you're wondering what is DER encoded object, it's basically a tree of tag length value triplets. So AS, when encoded, will look like this. The exact byte values are not very important. The important thing to notice that is it's a tree. So you start with the root node being the digest info. The second child node would give you the actual hash of M. The first child node of digest info would give you the algorithm identifier, which in turn contains two more child nodes. The first one being the object identifier OID, which tells you which hash algorithm to use. And the second child node would be the algorithm parameter. And you should also notice that these length variables in this tree, they add up from the leaf node all the way up to the root. So now the verifier given S, M, and public key. The verifier computes, takes S, computes R equals to S to E mod N, which R should look just like K, obviously. And then the verifier has to first check whether R is well-formed, and then compute hash of M, and see whether it matches with the hash inside R, right? So that's rather easy. So it turns out the problems happen here, right? The well-formedness check of R, turns out there are all kinds of leniencies going on, which brings us to Bleichenbacher's low exponent attack, right? So this is yet another crypto attack attributed to Daniel Bleichenbacher. So I believe at Crypto 2006 RUM session, he reported that some implementations would accept a malformed R prime. So R prime looks a lot like R, but with garbage bytes added at the end that are not being checked by the signature verifier. So he figured out that with this, you can actually do a existential forgery when the public exponent E is small, which means that an attacker can generate signatures for arbitrary M without possessing the private exponent. So this was one of the contributing factors to the push for using a bigger E. And, but on the other hand, smaller E's are more efficient for the signature verifier. So E equals to 3, for example, has been prescribed in many different protocols. Say, for example, in DNSSEC, they recommend using E equals to 3 so that the verifier is easier to verify signatures. So why was the attack possible? Right. The root cause of the problem is that some signature verifiers would accept a malformed input with some garbage bytes being unchecked. And this actually can happen in many different locations, not only at the end. And a longer modulus in this case would actually make the forgery attack easier because the attacker will have more garbage bits to choose from. And a longer modulus can also be used to handle, say, longer hashes or a slightly larger public exponent. So to find this attack, basically what we want to do is to see how input bytes are being checked on the verifier's code, right? If there are enough unchecked garbage bytes, then an attacker can potentially exploit these to do signature forgery. And this is actually a problem well suited for symbolic execution, right? So in this paper, instead of relying on manually crafted concolic test cases, we show that you can actually kind of exploit the structural format of this padding scheme to automatically generate concolic test cases, right? So the key observation here is that the size of the components, they somewhat exhibit a kind of a linear relations, right? So if you think about it, all the components, the size of them together should add up to exactly the size of modulus. And in the benign cases, the DER length inside the ASN1 object, they add up from the leaf to the root, right? So what we do here is we programmatically capture these kind of linear constraints, and then you ask symbolic execution to kind of on the fly find some satisfiable solutions. And based on those satisfiable solutions, we automatically pack symbolic and concrete components into the test buffer. And then with these concolic test cases, we can somewhat easily extract and abstract the signature verifier's verification logic in the form of formulas. This is a very useful abstraction because it tells you what and how things are being checked inside the signature verifier's code. And with the help of SMT softwares, we can automatically kind of cross-validate different signature verification implementations and see if they kind of agree with each other. And in this paper, we also try to make improvement in terms of making root cause analysis easier. So what you want to do is, if you observe some buggy behavior, you want to be able to locate the piece of code that imposes incorrect constraints, right? So basically, trying to go back to the code from the formula abstraction. So for that, we introduce a mechanism called constraint provenance tracking. So basically, you keep a mapping between the clause of past constraints to its own source level origin. And in the paper, we show through some experiments that this only incurs a tiny space and time overhead. Right? So we applied our approach into testing 15 open source implementations of PKCS version 1.5 signature verification found in many different libraries and software. And we found that 6 of them are overly lenient, 4 of which would be susceptible to the Bleichenbacher style kind of signature forgery attacks. And in the discussion of signature forgery, I would assume E equals to 3 and SHA-1 hashes, but the attacks can be adapted to handle longer hashes. So first, we found in OpenSwan that it actually ignores all the padding bytes. This is a rather simple oversight, but severe implication, because it's exploitable for signature forgery. So the attacker can use this malformed R prime and hide the garbage bytes in the padding. So now the attacker wants to find A and B such that the most significant bits of A cube would give you what is needed before the garbage bytes. The least significant bits of B cube would give you what is needed after the garbage bytes. And the remaining terms would stay inside the garbage, being unchecked. And with A and B found, the fake signature is simply A plus B. The exact algorithm for finding A and B can be found in the paper. Fortunately, the maintainers of OpenSwan are very responsive. So after we reported the problem, they quickly fixed it. In fact, one of the fake signatures that we sent to them, they took it and made it into a unit test. So in StrongSwan, we found that they're not checking algorithm parameter. This is a classical flaw also found in GNU-TLS and Firefox many, many years ago. And this is exploitable for signature forgery because the attacker can simply hide garbage bytes inside the algorithm parameter. And you can follow the OpenSwan attack algorithm by adjusting what A cube and B cube represent to generate fake signatures. The second problem we found in StrongSwan is that they're not matching algorithm OIDs exactly, which means there would be some garbage bytes, trailing garbage bytes in the OID that are not being checked. So interestingly, the matching logic of algorithm OID inside StrongSwan is a variant of longest prefix match, which means that the correct encoding of algorithm OID on the left-hand side and the incorrect one on the right-hand side with some extra garbage trailing bytes would both be recognized as the correct OID of SHA-1. So knowing this, the attacker can exploit this by hiding garbage bytes after the correct OID. And again, follow the OpenSwan attack algorithm, adjust what A cube and B cube means to generate fake signatures. Fortunately, again, the maintainers of StrongSwan are very responsive, so they quickly patched this problem after we reported our findings. So you might be thinking that, well, E equals to 3 doesn't really occur that frequently in the wild. While that might be true for X509 PKI, I guess in the ecosystem for IPsec, there are still key generation programs that forces, say, E equals to 3. And since both OpenSwan and StrongSwan are popular open source implementations of IPsec, depending on the actual deployment scenario, the attacks that I have described may be used to break authentication in some IPsec-based VPNs. And then in AXTRS, we found that it accepts trailing garbage bytes. So the original Bleichenbacher 06 attack would simply work. On top of that, we found that AXTRS ignores the algorithm identifiers. So given the encoded AS, the parser code would simply skip over this chunk that tells you the algorithm identifier. We suspect that this is probably because certificates already tell you which hash algorithm to use. But just because you know hash algorithm from the outside doesn't mean that this can be skipped. So the attacker can use this malformed R prime and hide the garbage bytes inside the algorithm identifier that are not being checked. And again, using the OpenSwan algorithm, a adversary can generate fake signature. Moreover, we found that AXTRS trusts the declared ASN1 DER length without any sanity checks. So what that means is that given the encoded AS, an attacker can put absurdly large value there to induce the signature verifier into performing some illegal memory access. So as a proof of concept for a DOS attack, we gave Z a really large value, and we managed to crash the signature verifier. And we developed the patch for AXTRS. It has been accepted by a port of AXTRS for ESP8266, but we are still waiting for the upstream maintainer to respond. Some other leniencies include, say, lax DER length checks found in, say, matrix SSL, which means many possible values for these DER lengths would be accepted by the signature verifier, which means some bits inside the middle of AS can take arbitrary any values, but they don't seem to be long enough to mount a meaningful signature forgery attack. And variants of these leniencies were also found in embeddTLS and libtomcrypt. Fortunately, even though we don't see an immediate attack, the maintainers of matrix SSL have patched this problem and changed how they verify signatures. So to conclude, RSA signature verification should be robust regardless of the choice of E. Flawed verification can break authentication in different scenarios. To analyze this problem, we extend symbolic execution with automatic generation of concolic test cases, and we introduce a mechanism for tracking provenance of constraints. And in this paper, we found new variants of Bleichenbacher's 06 attack after more than a decade. And we have 6 new CVEs assigned, along with many other unwarranted leniencies. So with that, I'll conclude my talk, and I'll be more than happy to take questions from the audience. Thank you.
Hi, this is Hamed Surush from Xerox PARC. Thanks for your interesting talk. So I have a question about the SMT. Could you comment on which SMT solver you used, or if you developed your own, and what motivated that decision? First, I have another question.
I couldn't hear the second part.
Oh, and what motivated your choice of SMT solver that you used?
Oh, so I think in this work we were using Z3. Okay. So for symbolic execution, we're using CLI. So the newer version of CLI, I think, came with Z3, so we just used the same.
Okay. And did you modify the source to implement the provenance tracking?
Indeed, yes, we did. So we modified CLI and to add that provenance tracking.
Okay. And will you release that source code?
We're planning to, cleaning up the code base. And
great. Thank you.
Sure.
Hi, Roland Yap, NUS. I was just wondering, the attacks which you mentioned,
yes,
can they be automatically derived from the constraints, or do you have to do some manual work?
So I mean, symbolic execution, or I guess even fuzzing, they tell you what is being handled inside the program, but they don't tell you how to do crypto attacks, right? So
right. So
yeah. So after we know the vulnerabilities, we try to come up with crypto attacks to generate fake signatures. So that is kind of a manual. Yeah, math exercise. Thanks. Thank you.